Right. I like to start most of my presentations these days with a little anecdote, which is kind of funny, but which also, gives you a bit of background on where I come from and how I perceive the field. So I'm not sure if people are familiar with the screenshot, with the movie that this screenshot was taken from. It's called Interstellar, and it's a movie where astronauts, discover outer space and are accompanied by smart robots, basically, as you can see here on the right side. I'm not sure if you can see my mouse, actually. Let me try to see if the laser pointer works. Can you see that? Okay, perfect. Right. Um, and so I watched this movie a couple of years ago, and something like 5, 6 years ago, and I told my partner at the time that I think it's going to take years until we reach that level of AI, because astronauts could converse with these machines like they do with other humans. And well, I was wrong. I think in terms of conversational AI, we've come quite some way until today, and conversational AI has reached almost human level performance. But I think what is striking here is that this scene here plays on a planet that is light years away from Earth. And to have an AI that works that well light years away from Earth, you really need big efficiency, right? Because you need an AI that can work with minimal energy on minimal hardware, ideally. And to achieve that, we have efficient AI and efficient language modeling and efficient natural language processing. And that is what we will talk about today. Here's a quick overview. I will first start with an introduction in general on low resource NLP and efficient NLP, paving the way a little bit for the topics that we'll cover later, talking about dimensions of efficiency, why we need that. I will give you a big range of motivations for why efficient NLP is important, and then we'll focus on two topics, one of them being data efficiency, so learning with few data, and the other one being model efficiency, so learning with few parameters, and if I don't have massive compute available. Before we dive in, what this talk will be is hopefully a nice overview of the most common approaches to model efficiency and data efficiency. So if you're not familiar with the topic, I hope this talk will provide you with something to go back to if you want an overview of what techniques there are. I will not go in depth into super cutting edge applications on highly specific methods or highly or tasks, because I'm assuming that the audience is also has a varying background. So I won't give you here a complete summary of all the ideas that the field has for model and data efficiency, also because it's a highly researched field nowadays. So we're really just looking at the tip of the iceberg here. For more specific topics or topics that I deem more relevant, I will present some results of papers using them successfully, but I will explain the methods on a high level so everyone can hopefully understand how these methods work and what methods there are. All right, let's start. So as most of you might know, if you've been working with AI, there has been a trend in recent years in language modeling to make models larger and larger. Why? Because there are certain scaling laws that show us that to really reach human level performance and conversational performance, we need models to be very, very large. And that leads to a incredibly sharp increase in model sizes. So we started here with an Elmo model in 2018 with only 94 million parameters. And we're ending here with models like GPT-3 in the hundreds of billions parameters. So you can see the y-axis here is logarithmic, actually. So it's a vast difference. And then if you look at GPT-4, it's supposed to have 1.8 trillion parameters, which is 10 times larger than GPT-3. And of course, it is a problem because most people don't have the hardware to run such models. So the sheer size of these models poses big problems for people that want to use them. Also, multilinguality is a big problem. I like to show this graph a lot. What you see on the left side is the NLP solutions that we have per language. And you see that English make up 2/3 of available NLP solutions on the market. While, as you see on the right side, more than 2/3 of people in the world do speak a low resource language as first language, and only 10% of people do speak English as a first language, with 23% European languages. So here it's kind of even. So you see there is a big discrepancy between the NLP solutions that we need worldwide and the NLP solutions that we actually have, which means that is a thing that needs to change, right? And the problem is, of course, that low resource languages, as the name says, usually don't have the data to train very big models, which is a problem because it results in us not having any models for such languages. There's multiple views on that. So you can also, if you look at dataset availability, see a similar picture. What you see on the left here is the amount of speakers of a language versus the amount of, or the number of Wikipedia articles of that language. So you see that even though there is roughly the same amount of English and Chinese people, people that do speak one of these two languages, the amount of data that is available for these languages is vastly different. And I'm using Wikipedia here as an example, because especially for low resource languages, this is still like one of the first resources that people turn to because it's so large and because the language is fairly good, right? And you can see that the amounts of Wikipedia article that we have here are vast for English, and for anything else, they're comparably small. So there is no data for such language. And we see the same picture if we look at the number of data sets and models for specific languages on Hugging Face, for example, which is one of the most famous and most used hubs for pre-trained models and for data sets in the area of language modeling, natural language processing. So you can see that English has vast number of data sets and models, and already the second most resource language is only a fraction of English, right? So even for French, Chinese, German, Russian, etc., we only have a fraction of the resources that we have for English. So there is a big imbalance here. Well, I have some more motivating examples, not that they were needed, but if you look at one of the most used data sets for pre-training also large models, it's called the Pile. It's an 800 gigabyte data set of diverse text. This is almost 100% English, right? And if this is the scale that we need to train the really large language models, the Pile is used for that. What do we do with less resource languages then if we don't have these massive amounts of data? So there's problems over problems, right? Models get incrementally larger. They need more space. They need more hardware. And they also need more data. They cover mostly English so far because that is just where we have the data, and some few other languages. And we don't have data for these low resource languages, which is a problem because research has shown that more training data basically means more powerful models. That means we need a plethora of data for the performance that we are expecting from large conversational models. But what about a long tail of languages with very few data and countries with less resources, for example? Well, this is where low resource and efficient NLP are trying to come to the help. So what does low resource mean? Well, it basically means two things. Low resource either means we have very little data and need to make the most out of these available data, or we have very little compute, very little hardware, so we can't train the really big models on our data, but we need to scale down. And in reality, often these both cases come together. We don't have lots of data and we don't have powerful hardware. There is these two, problems, or these two directions in efficiency or in low resource methodology correspond to strands of research. One of them being data efficiency, you can see on the left side here, and the other one corresponding to model efficiency. I'm calling the slide symbology because you will see in the top right of most of the slides that I'm presenting these 4 symbols with a couple of them grayed out. So you can see what dimension of efficiency the method that I'm currently presenting reflects, basically. For the scope of this talk, I will not focus a lot on faster inference, just because I feel the question of how fast inference has other dimensions and other problem dimensions that I won't cover here. It's all connected, right? So if you have little data and little hardware, there is strong interrelations between these two scenarios. For example, if you have little data, that means that a model that I have overfits very, very fast. If I have very few data and I throw these at a very large model, or at any model, it tends to overfit, which means that I need methods that learn more cautiously and not with a brute force approach, which are typically smaller models, right? And smaller models mean I need less hardware. So there's a connection between having few data and little hardware, but it also goes in the other direction, right? If I have only small hardware, I can only use small models. And I can just train less because my hardware might not be as fast, right? If I can't train as much, that means I need as little data as possible with the highest quality as possible, which means I need small data, right? Also, smaller models have a lower capacity, which also typically means that it is more favorable to have less data with a better quality to train them. So we also have connections into the other direction. Right. With this background in mind, let's look into the first topic which is data efficiency. I will cover some approaches here. The main focus of the talk will actually be model efficiency, but I will also present some approaches here on data efficiency. So the idea is, of course, that you want to have methods to find the most valuable data, or to make your data as good as possible, or to take the most out of the data that you have. There are very, very many approaches towards that, but I think the three main strands can roughly be split into pre-filtering data. If you have data and you need to find the valuable data points, online methods to pick the right data, which is similar but happens during training, and then data augmentation if you don't have lots of data and you want to get more data. We'll start out with the pre-filtering. This is a topic that is especially relevant in the light of pre-training and training very large language models, because the current paradigm is more equals better, right? And if we look at the pile again, for example, we have this number of documents, but the problem is, although the pile is supposed to be a very clean data set, it's still super noisy. We have lots and lots of duplicates, as you can see here on the right side. So what the graph shows is the number of instances that only appear once, the number of instances that appear twice, 3 times, etc. And you can see that not even half of the data points, that means texts, that we have in the pile are actually unique. There's lots of duplicates, or, which is worse because they're not so easy to detect, near duplicates, right? So where a couple of words are exchanged. And that is, of course, also a problem because we have a big leakage between training and validation data if the validation data are just split off at random. So it's very hard for us to tell how well our models work. All right, so what research has shown that deduplication here helps a lot. So research currently investigates smart methods to find duplicates or near duplicates in training data. And it has been shown that this means that models are forced to learn deeper reasoning rather than just copying from the training data. So it has been shown that if training data are duplicated, models tend to just copy whatever they find in the training data into the output. And it also means we need less data points, so the training becomes faster. Well, what about fine-tuning? Can we also do filtering during fine-tuning? Well, there is similar trends to pre-training, but it's a bit more challenging because fine-tuning data are typically much more diverse and more specific than pre-training data. But one method that people use is, for example, adversarial filtering. The idea is quite straightforward. So imagine you have a data set of fine-tuning data, and what you want to do is you want to split. So you want to make that data set smaller, right? So your end goal is to get the most valuable out of these data. The most valuable ones from these data points. So what you do in adversarial filtering is you prepare a number of training validation splits, right? So you have n training and validation splits here. And then what you do is you train n models. So on each of these training data sets that you have created from your original data, you train one model, and you can evaluate it on the validation data or tune hyperparameters, for example. What you then do is you, across the splits, try to find out across all validation data, which are the data points that are the easiest, right? So if you have n models and you have one data point in your validation data that is correctly classified by all of the models, you can assume that data point is quite easy to learn, right? And what you then do is you delete these easy data points, and then delete a couple of them, and you have your filtered data set, and then you return, you repeat the cycle basically until you have a very small size of data reached. And this has been shown to work very, very well. So for natural language inference, for example, which is one of the most common tasks for evaluating language models and downstream performance, people have found that you need only 2% of the training data to perform on par for some of the data sets, right? So this is very, very relevant if you have a larger amount of data and you want to cut it down to something smaller to make the most out of the available data. Of course, this is interesting for low resource languages when you create data sets to find the challenging examples, right? So imagine you have an unlabeled data set and you want to find out what are the examples that I really need an annotator to look into. And this is very similar then to active learning, which we will talk about later. Right. Online methods to pick the right data, which is active learning. It's similar to adversarial filtering, you want to pick the right data, but the difference is that you do so during the data collection or during the labeling. So this is typically used in situations where you have a larger pool of data that are not labeled, and you have a very small pool of data that are labeled. And then you have an expert that can, label new data points for you, but maybe the labeling is expensive, or, for a low-resource language, you only have one annotator. So you need to find out which data points do I label rather than labeling them all. So what you do is you start with a very small pool of labeled examples, and you train a model on these. Then you use the model to automatically label all your unlabeled data. And then comes the trick. You kind of pick challenging examples from the unlabeled data. So you look at measures like, model confidence, data distribution, etc. And you only pick the instances from the data which you think are most valuable. And then you pass them onto a human and let the human do the manual labeling. You add the manually labeled data to your training data set, and you repeat the cycle until either you reach a certain performance, you have enough training data, or the human becomes too expensive, for example. How do you do that? Well, a very simple way to pick the challenging instances, and that is the main black magic that is in active learning, is to use uncertainty. For example, the entropy of a classifier, which means the uncertainty of your model about the labels that it is assigning. And then if the classifier is very uncertain about the labels, that means this is an example that will help the classifier a lot to get better. So that is what you would use here. Active learning was successfully used for machine translation or language learning, for example, and it is used, I would say, a lot in practice with the human in the loop. There is not too much research work on it, on like end-to-end active learning, just because it's so application specific, and it really depends always on the configuration that you have with annotators. But there is a lot of research, for example, on how to pick these really challenging instances, and a plethora of work on that. Another thing that people do is curriculum learning. The idea is very simple. So when humans learn, we usually start with simple things and then go more complex, right? We don't look at all examples at once. And the idea of curriculum learning is to apply this to machine learning in order to maximize data efficiency in terms of their data utilization, right? So of course, this doesn't reduce the amount of data needed, but it maximizes their productivity. So imagine you have reached, a specific amount of data that you can't increase further. And then you ask yourself, okay, so how do I use these data in the best possible way? And then curriculum learning might be the way to go. As the intuition is super simple, the implementation is also very simple, right? So you usually split your data up into bins, from tricky, not so tricky, sort of simple, to super simple. I'm just making that up here, of course. And then you have machines learn, right? So you either say, okay, you have 4 training cycles, you learn simple to hard, or you learn hard to simple. And actually, funny enough, the latter has been shown to work often better for machines. So often machines learn better if you show them the most specific, the most difficult examples first, and then go to the simpler ones. So they kind of learn the other way around than humans do. So this was, for example, successfully used in efficient pre-training, with the very simple idea to just sort examples according to length, right? So you have very long sentences during pre-training, medium long, medium short, and short sentences, and then you can train short to long, so like simple to hard, or hard to simple, meaning long to short. And what you can see here, that sorting by length works well already. If you look at what you can see here is downstream performance on actual tasks. You see here a vanilla model, I think it was a BERT model. And you can see that we outperform, on some of the tasks already quite significantly on MRPC. For example, on QQP, we outperform the BERT base model. But you can also, have more sophisticated text complexity measures, and that further improves performance. So you can see that we improve on the base model here by almost 2% just by resorting the training data during pre-training, right? So that works very, very well, and it really squeezes out more performance out of the few data that you might have. Right, so this was pre-filtering and online methods to pick the right data. Now I want to talk about data augmentation very briefly. Data augmentation is a field that has been around as long as we do machine learning, which is quite a significant time now. So I'm really just, talking about the tip of the iceberg here. Some very common methods that you might have come across is back translation, for example. So if you have data in one language and you want to increase the amount of data that you have for that language, say it's a rare language like Maltese, for example, what you can do is you can take a machine translation model, you can translate your data into, say, English, and then translate them back into Maltese. This has been shown to work very well as a data augmentation technique because the machine translation model always, alters small details in the formulations, and it kind of adds paraphrases, for example, and this has been shown to work very, very well in practice. In fact, this is also a thing that is used a lot in applications. So I worked in industry, for example, for a company that is doing AI assistance for cars. And this was like one of the main things that we always did when we trained our models is we back translated all the data we had to just increase the amount of good quality data that we could train our models on. There's also adversarial methods where the idea is to find inputs that are similar to the original by altering parts of the representation to make the model more robust to noise, which is also a way to make the most out of the available data. So what you can do, for example, is using dropout on the input. So masking out random dimensions of your input to increase model robustness. And then there's other automated methods that work surprisingly well. You have like language model-based token replacement. So where you take an already pre-trained language model and randomly let it replace tokens in your text, for example. It has been shown that it works very well to just delete tokens or to shuffle them, which is kind of straightforward, but really does the trick in quite a few cases. So actually, we're doing a lot of research on data augmentation also, and we often find that these simple methods work already so well that they are hard to beat. So that is, although it sounds naive, still a thing that people do a lot. One thing that has become more relevant now is what people kind of call now LLM distillation. And if you have a machine learning background, then you will see that this, or you might, share my opinion that this is a weird term because distillation was always meant to be a specific machine learning technique where you have a student and a teacher network and a common loss. And but people call also now a new technique distillation, which is basically just to use a large language model to generate more data. In this example, by paraphrasing, right? So you pass data to a language model and you say, reformulate this text. You can even use ChatGPT for that, right? And then whatever comes out, you use as a kind of a paraphrased additional resource. So you kind of double your data size. You can also make that smarter by saying, okay, I have a large language model, label a very large unlabeled pool of data based on some examples, maybe some in context learning, and then I train a smaller language model on the data that the bigger language model has labeled. So I kind of try to imitate the large model on the data that it has generated, and people found that this works very, very, very well. There is actually recent work comparing the cost of using human annotators versus GPT. And GPT is, of course, much more cost efficient than humans, especially if the budget is low. But they also find that a kind of co-creation is most efficient, which then goes into the direction of active learning again, right? So you use the language model to label whatever it can, and whenever it's unsure, you ask the human. There's also applications on using large language models, for example, as an oracle during active learning, which is also a thing that we work on at DFKI, for example. And then just to mention a very obvious topic here for the sake of completeness is transfer learning. It's somewhere in the middle between data and model efficiency because it also means you can use smaller models. And this idea has been around for quite some while, and it's actually one of the central paradigms that also modern large language models use. So the idea is basically that you train a higher resource model on a large data set that is somewhat similar to my target data. So it might be, a similar task, question answering, information retrieval, or the languages might be related. You have Maltese and Italian, for example, or, you name it, any other type of related languages. And then you use the weights that you've learned in the high resource language model to initialize the low resource language model. And then it has been shown that the low resource language model needs a lot less training data to reach a good performance because it has so much prior knowledge from the larger language model already. Right, and this basically sums up the first part, which is data efficiency, where the idea is to find the most valuable data, to make the most out of the available data, or to increase the data, the data that you have. So we talked about pre-filtering, online methods to pick the right data, and augmenting data. But as I said, this is just the tip of the iceberg and a very rough overview over what is done. Right, with that, let's move to model efficiency. As I already said, the main things we will look at here is faster training and smaller models, and not so much at faster inference, although some of the methods that I will present also result in a faster inference, so faster performance of the model at runtime. Of course, faster training is often better if strong hardware is not available also, because the slowness of the hardware is counteracted. You know, if my training is very efficient and I don't need as much time, and I don't need it's not as critical if one epoch of training takes longer, for example, because my hardware is weak. So I kind of can counteract the slowness of a hardware with a faster training approach. And then, of course, if I have less parameters, that in generally results in a faster and slimmer training, both can be useful for smaller data sets as well, right? So if you do a faster training, then the model can make more out of the available data and can train more efficiently. You can run more epochs. And if you have less parameters, then often the model's capacity better matches the available data. So you kind of have a reverse effect here, although there is, at least for the latter, no guarantee. Because it's so ubiquitous and so important, I will mostly focus here on parameter efficient methods for fine-tuning and pre-training, also called PEFT methods, which is just a kind of abbreviation that is used a lot by Hugging Face. For example, there's a famous PEFT library which implements all of these methods. For example, adapters, prompt tuning, prefix tuning, LoRa, and adapter and prompt transfer and fusion, which is what I will cover here. We start with adapters. So if you have been using language models, you might have seen the picture on the right. You might know that most modern language models are based on a transformer architecture, which is an actually quite straightforward neural network architecture that is just comprised of a couple of central elements that are then just repeated very, very often, you know, to get the model capacity. These elements are a multi-head attention, feed-forward layers, and layer normalization. And then you have also some residual connections here. So this is kind of, you know, a straightforward architecture for somebody that works with deep learning models. This is nothing fancy. Now, the idea of adapters is basically that you add a small set of parameters into a language model. So you add another, you know, small layer inside each transformer layer, and then you only train the layers that you have added, and you leave the rest of the network frozen. You can use this basically for pre-training and fine-tuning and for any tasks to adapt your language model. And this is very efficient because the amount of parameters that you add with an adapter here is much smaller than the parameters that you already have in your full network, which means it's much more efficient than fine-tuning the whole network. And most importantly, it means that you can use the same base model for a wide range of tasks because this is modular, right? So you can train a set of adapters for 5 tasks and then use the same base model for all of these tasks. So this is, for example, very important if you want to deploy, say, a language model on a mobile device, for example, where you don't want to have, you know, like 5 models for 5 tasks, but you might just want to have like one base model and then have 5 adapters that kind of specialize the model into a specific direction. How does an adapter look like? It's also very, very simple. It has a bottleneck structure in its most basic form, which basically means I force the model to simplify, right? So when I get a big vector in, I have a down projection matrix, which kind of compresses the vector into something smaller. I have non-linearity, and then I decompress the vector again and make it, you know, larger again. So I match the dimensions of the output here, and that's it in the basic form. You have a residual connection here, so you have the potential to leave, you know, to have information flow from the top to the bottom directly, but it's very, very straightforward. How do you use it? Well, so if you want to use it for fine-tuning, for example, the way it works, you take kind of a base model, in this case, a BERT model that you freeze, so you don't train the parameters of the BERT model, And then you just add your couple of adapter parameters and you have question answering data, for example. So you can train a question answering adapter. You know, the flames here mean that the model is trained, of course, that the adapter is trained. And then the fun thing is you can use the same base model and now throw reference data at it and train another set of adapters. And then you have a reference kind of a model that is capable of solving reference resolution, right? And so it goes on. You can use named entity recognition data, throw them at the same model, use another set of adapters, and boom, you have a model that can do any named entity recognition. And you can use the same base model for all of these tasks. So it's super, super parameter efficient. And it leads to highly effective models for single tasks. And now what is cool is you can also use that for pre-training, which basically means you can make a multilingual model an expert for a single language, right? So if you have for example, a multilingual base model that has seen hundreds of languages, but you want to, develop your model for German, you don't need to start from scratch. You can use this multilingual model. You can add, we call it language adapters, and then you train the model on its pre-training tasks. So here it could be masked language modeling, right? So if you have German data, you can say, okay, my kind of input to the model is ChatGPT ist ein, and then the model has to predict Sprachmodell, right? And if I pre-train a model on that, then I have a multilingual BERT model, a multilingual base model that is an expert for German. And I can use the same model to make an expert for French, for example, by using French data, ChatGPT et un, and then the model has to predict modèle de langage. And the same for English, right? You can say ChatGPT is a, and then you can say it's a language model. The model has to predict that. So you can try to specialize one base model in different languages. And well, this works crazy well. So what you see here on the left side is the performance of such adapters on the GLUE benchmark, which is like the most used, or which was until a couple of years ago, the most used benchmark for evaluating natural language understanding capabilities of models. And what you can see here is the difference in accuracy to the base model that just uses the full model for fine-tuning. And on the x-axis, you see the number of parameters that are used for the adaptation. And you see that with a minimal number of trainable parameters, you are as good as fine-tuning, right? So you can see that, if you are here, you are already at a performance of the base model, even if you have just a fraction of the parameters. And this is a logarithmic scale, right? And you can also see that like adding more adapter parameters doesn't really improve it anymore. You just need a very few and you're just very good already. We also see that it works very, very well for multilingual transfer. So what you see here is a model that is only trained on English named entity recognition data. And you see that MADIX, this is the performance of the multilingual model with language adapters, outperforms all the other models by far. And this is especially, and this kind of holds across languages, right? So you can do language transfer across many, many languages with these language adapters, which is why they are used up to date a lot. Of course. So a reminder, these are adapters, right? You add parameters inside of the model. And now smart people ask the following question: why the heck should we add parameters here exactly? There could be any other way to add parameters. And then with the boom of very large language models, people realized, well, they focus a lot on the input, right? So prompting is a new research direction now, formulating a question that you have to a very large model in a smart way. And this is the basic idea of prompt tuning, or also called, or like with its variation, prefix tuning. The idea is that you just add parameters on the input level and you kind of prepend them to the actual input, like so. And then this behaves somewhat like a handwritten prompt. That is where the name comes from. But you tune these parameters on the input level on a specific task at hand. So the idea is the same as with adapters, but you move the parameters from inside of the network to the input level. Prefix tuning is a similar idea where you add kind of parameters on intermediate levels. So in between the layers, you also don't need to go inside of the model architecture, but you just add more parameters at each layer, but not inside the layers. There's many more names of that. Soft prompts, p-tuning, there's p-tuning v2. These are all similar ideas with like very slight variations. And the bottom line is it works crazy well at even 0.1% of the parameters of fine-tuning. So we compare here fine-tuning, that is the red bar, p-tuning, so one variant of that, and p-tuning v2. And if we have a base model of 330 million parameters, with only 0.1% of the parameters of full fine-tuning, we reach the same performance. So this is very, very efficient. And most importantly, it outperforms fine-tuning in low data settings. So that means, here we can see again that parameter-efficient methods are often also very good in low data regimes. What you can see here, prefix tuning is the orange line, fine-tuning is the blue line. And you can see that if you have only like 100 to 500 training instances, prefix tuning outperforms fine-tuning by far. So it makes the most out of the available data. Very briefly, because it's used a lot now, there is variations of that called LoRa or Q-LoRa for low rank adaptations of language models. The intuition is similar to adapters, but they are better parallelized. So what you can see here is that adapters are a bottleneck structure, so there is very few computations flowing through them, which means they're kind of, or they're comparably slow to actually train. And LoRa kind of parallelizes the execution and the training, which means they are good in all 4 dimensions of efficiency, by the way, because they also make the inference very, very fast. So the basic idea is that you learn an update matrix rather than an additional layer, and then you add the update matrix to the weights of the original model. And as this is so efficient and so good in all dimensions of efficiency, there's also many variations of that idea now. There is a great blog post on this. I'm just realizing I'm not sure if we're sharing the slides, but if you just Google for it, I'm certain you will find it. Right. So we already saw that transfer learning with adapters works, right? If we use the language adapters, for example, we can initialize language models for other languages here. So this seems to work. But what about prompts? Well, so the idea would be that I have prompts that I tune for a task A, and then when I want to, tune my prompts for a task B, I can just initialize them from task A and then continue training. And it has been shown that this works very, very well. I just give you one example here. So what you can see here, the method is called SPOT. I'm not sure what the acronym was for, but you can see that for superglue, for example, you outperform a base model by 7% with a fraction of the parameters, again, of course. And it's pretty cool because you can see that then if you compare the prompts across tasks, which is done here, so you have the vector similarity between the task prompts, you see that similar tasks have similar representations. So what you, for example, have here is complex question answering, right? And you can see that, for example, HelloSwag and Cosmos QA have similar prompts. So you can see that the prompt tuning for similar tasks leads to similar prompts here, which is kind of cool in terms of interpreting what these prompts encode. All right, and this brings me, I think, to the last topic block here, which is kind of the most fancy and most advanced technique that is used in path methods. It is based on the observation that, okay, transfer learning seems to work, but it has the central problem that we always need to know what to initialize the models with, right? So I need to know which tasks are similar, which languages are similar, so I can initialize a model with the weights that I have learned from somewhere else. And the question is now, can't we make the model choose? Can't we make the model choose how to initialize? And yes, we can by using fusion. The idea is quite straightforward, right? So rather than initializing, for example, an adapter with the weights of another one before continuing to training, what I can do is I can use a fusion layer, and I can input into that fusion layer all kinds of pre-trained adapters of diverse languages or of diverse tasks that I might have pre-trained. The fusion layer internally, you don't need to understand the picture completely, but it's basically just an attention layer, right? You have a value matrix, you have a key matrix, and then you have the query, which is initialized from the actual input. So the idea is basically to say, okay, the model sees the input that it has to process, and then it learns which adapter to attend to and which adapter to take the information from for the current processing. So it's a smart way of learning, of kind of transfer learning here with adapters. And it works very, very well. So again, what you can see here is that it outperforms full fine-tuning both in a single task and in a multitask setting. The same you can do for prompts. The idea is very similar. Again, you can say you fine tune prompts for 3 tasks, A, B, and C. And then if you have a new task D, what you can do is you can use prompt fusion, which basically means you learn a combination of the task A, B, and C prompts based on the input. That is where the attention comes from. And then you have a weighted combination that you can use as a prompt. What is done in practice, because people have just found that it works better, is that you reinitialize another prompt and then you combine that with the weighted combination, but the intuition remains basically the same. And here is yet again a very large table that shows how well this works. So you can see here, attempt is what this method is called, and it outperforms many other methods, including other PEF methods like adapters, like prompt tuning, by a larger margin. Again, what we see here is that it also works very well if we have very few training examples. So this was also the method that works best by far if you have only 32 training instances. This is, by the way, transfer learning for prompts, so it also outperforms that a lot. So it's very good for extremely low resource data settings, where you can see again that methods that are parameter efficient often also work very well in data efficient settings. Right, so this was a big overview over the main strands of research that we have in data efficiency and in model efficiency. I hope I got the point across that the two are highly interconnected, and that often if you are in settings where you have little data, it makes also sense to look into model efficient methods, because these often make the most out of the available data. In terms of model efficiency, we mostly talked about faster training and smaller models. Now there is a plethora of work on faster inference, so like shrinking models down to a very small size, so you can use them on a smartphone, for example, so they're much faster usable. If you're interested in that, some of the techniques that you might want to look into are quantization, for example, where the idea is that you encode model weights with kind of numbers that take up less space, or model distillation that I mentioned briefly in the middle, where the idea is that I train a smaller model that imitates a larger one, which again, ticks these 2 dimensions of efficiency. So it's all connected a little. Right, so this was my overview. Here are some main sources. There is quite a few review papers on the topic. There is lots of hands-on examples that you can try out in the PEF libraries and in the Adapter Hub library, which is the main hub for also pre-trained language adapters. So if you are working in a low resource scenario with low resource languages, chances are very good that there is already something pre-trained that you can just download and use. And with that, I say thanks a lot, and I'm happy to answer any questions you might have.